Hey everyone, welcome back to Calculus 3. This is going to be lecture 7 of the course. In this section we're going to move from what we had been discussing, which was sort of the introductory material needed for three-dimensional calculus, for vector calculus. And we're going to be moving into the actual calculus topics now. But I should say, technically, there is one more section that we need before we can get into the calculus of 3D space, and that is this section, vector-valued functions. So let's go ahead and jump into it. Okay, so we'll call this section 2.1, vector-valued functions. And so up until this point, we've defined vectors. Okay, we've defined what a vector is and all of the things related to vectors that are going to be needed. So, well, most of the things anyways, the dot product, the cross product. We've talked about components. We've talked about vector sums, scalar multiplication, etc. Right, lots of things. Right, so we've talked about a whole host of topics related to vectors, and now we're going to kind of get to the punchline here, sort of, almost to the punchline, really very close to the punchline. And so here we're going to define a new kind of function that is called a vector-valued function. Okay, so let's define a vector-valued function and see what they're good for. Okay, so a function of the form, okay, and it's going to look like this. It's going to be r, variable is t, and it's going to be equal to f of t times the I vector plus g of t times the j vector. Okay, a function of this form, right? This is the two-dimensional version of a vector-valued function, or there is also, of course, a three-dimensional version. We'll say it looks like this: f of t times I plus g of t times j plus h of t times k. Right, that's the 3D version. A function of either of these forms is a vector-valued function. Okay, a vector-valued function, okay, where the components, okay, the components are the functions, the real-valued functions, f of t, g of t, h of t, okay, these are real-valued functions. Of the parameter t. Okay, so a function of the form r of t equals f of t times I plus g of t times j plus h of t times k is called a vector-valued function, where the components f, g, and h are themselves real-valued functions of the parameter t. Okay, and so this is how these things are frequently denoted, you know, like something like this. It sort of depends on who's doing it, or something like that. But you can also denote them in the sort of the component form as well. These are sometimes denoted by, right, so you could denote them like this: f of t, g of t, like so. Or, right, the three-dimensional version would be f of t, g of t, h of t, right? So either way, right? So you can see that these, basically, a vector-valued function is just a function whose result is a vector, where the components are themselves real-valued functions of some parameter. Okay, now it is very important to keep in mind the differences between a vector-valued function and the real-valued functions that make up the components of the vector valued functions, right? So it is important to keep in mind the differences between r of t and the functions f of t, g of t, and h of t, right? So r of t is a vector. R of t is a vector. Right? F of t, g of t, h of t are real valued functions of real valued functions. Right? So they're numbers. Okay. Now, obviously, that's kind of why it works, right? A vector is basically an ordered tuple. You can kind of think of it like that, where the entries, the components, are real numbers, right? And so a vector valued function is just a vector, is a function whose result is a vector whose components are all real values. Okay, so it's kind of a different sort of thing. Now, what do these look like? Well, let's draw one in the plane. We won't try to draw it in three-dimensional space. It'll just kind of confuse people. But let's just like sketch what you might kind of want to have in mind when you see these. So let's imagine some kind of a curve here, right? And so you got a vector that comes up to this point, right? And this might be r of t1. And you got a vector that comes up to this point, and that might be r of t2, right, etc. Right, however far out these go. Okay, and now this is 2D space, so this is like your x, this is your y, and so this function would be a function of t, and it would be equal to f of t, comma, g of t, right? Where these are two real valued functions in themselves. Okay. All right, so that's what it kind of looks like in the plane. Now, you can easily extend this in your imagination to 3 dimensions, but it's a little bit tricky to draw them, right? Just because you have to have some like artistic abilities. But if you want, you can go on the internet and just Google vector valued function 3D space, and you'll find lots of visualizations of these things. Okay, now what about the domain of a vector valued function? The domain of a vector valued function, well, I mean, in general, the domain of a vector valued function would be the intersection of the domain of the components functions, right? So the domain of r of t should be equal to the domain of f and the domain of g and the domain of h, right? The intersection of those three, right? Because you got to be able to plug a single t into the function to a single t at a time, and so that t has to be defined here, it has to be defined here, and it has to be defined here. So t has to be defined for f, g, and h, and so that's the domain. So the domain of the overall vector valued function will be the intersection of the domain of the sub real valued functions. Okay. Well, let's see an example here, and then we'll talk about, in this specific example, maybe what the domain is. Okay, so let's take a look at something like this. So let's consider the function, the vector valued function, r of t equals the natural log of t times the I vector plus the square root of 1 minus t times the j vector plus k, the k vector. Well, let's say t times the k vector. Okay, so we'll put t in there. Okay. And so here you can see this is your f of t. This piece here, square root of 1 minus t, that's going to play the part of your g of t. And then down here, just t itself is going to be the h of t in this instance. Okay, so what's the domain here? Let's talk about the domain. So the domain of r, well, we know from what we just said, it's going to be the intersection of the domain of f, the domain of g, and the domain of h. Okay, now what is that? Well, the domain of f, that's the natural log function. Well, the natural log is defined for all non-negative numbers, right? So this would be like 0 up to infinity for that piece. What about the domain of g? Well, this is the square root of 1 minus t. And so this can be any number, right? So this is a real valued function, so we don't want imaginary numbers here. So the domain gets restricted somewhat. We can't have... So basically, you would say anything between 0 and up to and including 1. The square root of 0 is okay, so something like that would work. Anything less than 0 and you're dealing with, you have a problem. Anything greater than 1, you have a negative, right? So these two kind of give you the endpoints of 0. And what about this guy? Well, this is, you can basically say the domain here is all of the real numbers. Right, so technically, actually, you know, this could be negative infinity up to 1, right? That'd be okay. Any negative number you plug in there is okay, right? It'd be just 1 minus negative 2 would be square root of 3. So that's okay. But so what is this intersection? Well, you've got a lower bound here on 0, and your upper bound is on the 1, right? So the domain of R is the interval, half-open interval 0 to 1, okay, in this case. All right. Okay, and then this is also a nice introductory example of a vector-valued function. All right. Very good, very good. Let's do another example. Let's talk through some more of these, see if we can develop some good intuition about vector-valued functions. Okay, so let's try to sketch one of these. So let's sketch the plane curve represented by the valued function represented by the vector valued function, and here's the function, r of t equals 2 times cosine of t, right, that times the I vector, minus 3 times the sine of t, and then that times the j vector. Okay, and let's just concern ourselves with t's that are between 0 and 2 pi. Okay, so something like this. So given r like this, we can kind of, like if we want to sketch this, we're probably going to have to convert this into some sort of xy equation, right? So given r, right, so we're given r, okay, we can pretty much write the two parametric equations really quickly and easily. We can write the following. Basically, x is equal to 2 cos t, and y is equal to negative 3 sine of t. Okay. And from this, we can do a quick conversion here. Okay, and so these two would imply that cosine of t is equal to x over 2, and sine of t is equal to y over negative 3. Okay, all right, so that's pretty straightforward. And then we can plug this in, we create an equation from this, basically using the Pythagorean identity. So because sine squared t plus cos squared t equals 1, we get, what do we get? We get y over negative 3 squared plus x over 2 squared equals 1, right? And that basically gives us an equation that we recognize, and we can write it as x squared over 4 plus y squared over 9 equals 1. And so this is the equation of an ellipse. Right? It looks almost like the equation of a circle, but remember, in the equation of a circle, the denominators are the same. Right here, they're different. So this is the equation of an ellipse. Okay, and can we sketch the ellipse? Sure. Yeah, we surely can. All right, so here you've got your y-axis, and then we'll put the x-axis there. Now this is centered at 0, right? Because notice there's no x minus or y minus. Right? So it's centered at 0, 0, and it'll be, we'll say 2 over on the x-axis, and we get that from x squared over 2 squared, which is 4. And then it'll be 3 on the y-axis. Okay, so the center is here, and this thing kind of looks like this. I should have drawn it better. Oh, it's terrible. Let me actually space things out properly. I forgot we're doing an ellipse here, so it does matter when you draw it, obviously. So it should look, this will look better. So it kind of comes like this, goes down like that, comes up like that, and goes around. There we go. All right, and so it's centered here. Okay, and so this is x squared over 4 plus y squared over 9 equals 1. Okay, now what's going on with the vectors, right? So as t increases from 0 to 2 pi, what happens? What happens? Well, we can plug in values to see, right? So okay, so let's plug in t equals 0, for example. So r of 0, that's going to be twice cosine of 0 times I plus negative 3 sine of 0 times j. Okay, and so sine of 0 is 0. Cosine of 0 is 2. So this would be like 2i plus 0j, right? So when it starts, the starting vector is here at t equals 0. What happens if I plug in t equals pi over 2? We'll say, let's try to find nice numbers here. Well, r of pi over 2 would be twice cos pi over 2 times I plus negative 3 sine of pi over 2 times j, right? And so cosine of pi over 2 is 1. Oh, sorry, is 0, right? So you get 0i, and then sine of pi over 2 is 1, so this would be minus 3j. And so basically what's going to happen is the vectors are going to swing down, aren't they? The one we just calculated is down here. Right, and so you can imagine this is going to swing through the whole arc, and it's going to have a direction, an orientation. In this case, it's going to be a clockwise orientation. All right, so this function has a clockwise orientation as t goes from 0 to 2 pi. Okay, so that's important to know, the orientation of how this function moves. Okay, so that's the idea. It kind of moves in this direction. Excellent. Okay, let's do another example. Take a look at another example here. Let's in this case, let's start with a y equals a y is a function of x and generate a vector value function. Okay, so let's represent the parabola given by y equals x squared plus 1 by a vector valued function. Okay, represent the parabola given by y equals x squared plus 1 by a vector valued function. Okay, and so usually what we'll do is we'll just say, let's start by letting, this is a two-dimensional vector, right? So let's let x equal t to start with. Okay, all right, so then we'll say y is equal to t squared plus 1, right? Basically just a little substitution game. If x is equal to t, then you got an x squared plus 1, so let's make it t squared plus 1. Okay, so doing that, we have the following. Here's a vector valued function. R of t is equal to t times I plus t squared plus 1 times j. Okay, so that is a way to represent the parabola given by y equals x squared plus 1 using a vector valued function. Let's explore this a little closer. All right, so let's take a look at what we can do with this. So let's plot some points. Okay, so let's plot the point what happens when t is equal to -2, for example. Well, then we would have r of -2, and that's going to be equal to -2i plus -2 squared plus 1 j. Okay, and what do we get there? Well, we get -2 for the I component. And what do we get for the j component? So this would be -2 squared plus 1, which is 5, right? So we get that. What about the -1? Let's let t equal -1 and see what happens. R of -1. Right, so here we get -1i plus -1 squared plus 1 j. And here again, we would have -1 for the I component, and then the j component is 1 plus 1, which is 2. Okay, let's do one more. Let's let t equal 0. You can see we're kind of moving from the negatives over to the positives. So let's let t equal 0. So r of 0 is equal to 0i plus 0 plus 1 j, which is going to be the vector 0, 1. Right, and we could keep going like this. But let's see what does this produce in the plane. Okay, so let's draw xy components here. And we'll go 1, 2, 3, 4, 5, and then 1, 2, 3, 4, 5, like so. We know we're all in negatives here, or we're in quadrant 2, I guess. And so when t is equal to -2, we saw up here, the vector is -2, 5. So 1, 2, 1, 2, 3, 4, 5. So right about here, right? That's t equals -2. Okay, what about when t is equal to -1? Well, then it's -1, 2. So -1 over and 2 up is here. And then when t is equal to 0, we get 0, 1. That's here, right? And so what's happening, you can see, is it's coming down like this. So remember, this is t equals -1. This is t equals 0. So what do you suppose it's going to look like on the other side? Well, predictably, I mean, you can plug this value in, but what happens when we plug in t equals 1? We're going to get something right here. And when we plug in 2, we're going to get something right over here. Okay. right? And so this is what the vector valued function looks like for this particular parabola. The parabola here is being represented by the vector value function. All right, very good. Okay, cool. So those are a few examples. There's lots and lots of good examples to look at here. But let's move on to some properties of vector valued functions. Okay, and we'll see lots and lots of examples as we go forward. So hopefully any gaps that we maybe have in understanding these will fill in pretty rapidly. So the thing about vector valued functions, which is nice, is that because the components are all real valued functions, many of the techniques and definitions, and as we see, things like continuity and limits and such, are all preserved for vector valued functions. Okay, so many techniques and definitions used in calculus, math in general, used in the calculus of real valued functions, can be applied to vector value functions. And we'll see lots and lots of examples of these, but let's just take a look at a few, right? For example, what happens when you try to add or subtract two vector valued functions? Something we certainly do all the time in calculus when we're doing derivatives and we're calculating integrals, etc. What happens when you add and subtract vector valued functions? Do we get a nice predictable result? Well, let's see. So if I have two functions, r of 1 and r of 2, vector valued, and I want to add and subtract them, something we do all the time. Well, I'm just going to use the component form. This would be like your f1 of t and your g1 of t, and I want to add or subtract that to f2 of t, g2 of t. Well, what do? I mean, we just add the components. This is just a vector sum, isn't it? We've seen how this works. It's just a vector sum, right? So this is just going to be f1 of t plus or minus f2 of t, and g1 of t plus or minus g2 of t. That's all. So that's very natural and familiar, right? It's just the ability to add functions, and they're vector valued, just depends on the vector sum, which we talked about. What about the scalar multiplication? Another example. All right, what if I have some real number c and I multiply it times my vector t, my vector valued function r? Right, well, that's just the scalar multiplication, isn't it? Right, so it's just basically take the scalar, multiply it through. Right, and I get c times f1 of t, c times f2 of t. Right, so this is stuff we've seen. We're familiar with this, right? And this is obviously an important piece of technique that we'll use all the time in calculus, right? Think about when we were learning about how to evaluate limits, what we could do with constants, pull them outside. What about when we were doing integration? We could be able to pull a constant in and out, right? Same thing with derivatives, etc. Right, so the point here is just that vector valued functions, because they're based on real valued components, and we have a lot of we've explored a lot of the properties of vectors, and a lot of that stuff kind of you get for free, right? So the basic approach here is just really capitalizing on the linearity of vector operations, right? Just the linearity of the vector operations. Right? And so you get all of the addition, subtraction, the multiplication stuff. And another thing that you get is the definition of a limit. Right? So limits are defined for vector value functions as well. Okay, let's talk about that. What is the definition of a limit if you're dealing with a vector valued function? Right? So if r is a vector valued function such that, we'll just write it out here. So it's just going to be the familiar f of t times I plus g of t times k plus h of t, times j, that's a j, sorry, times k, right? So that's a j. Okay, so if r is a vector valued function such that it has this form that we're familiar with already, then the limit can be considered. So the limit of, as t approaches a, of r of t is going to be equal to the limit of the individual components. So the limit as t approaches a of f of t times the I vector plus the limit as t approaches a of g of t times the j vector plus the limit as t approaches a of h of t times the k vector, right? So very natural. Very similar to what we described up above here, right? So when we're just combining two vectors in like an addition subtraction way, you see that the property of the combination is basically delegated to the individual components, right? Similarly here, right, when we were trying to multiply this vector valued function by a constant, well, that activity gets basically delegated down to the components. The same thing is true for the limit. If I want to take the limit of a vector valued function, what I'm really needing to do is take the limit of the individual components, right? So this is the definition. Now, of course, this all depends upon f, g, and h having these individual limits, right? So we should say that this is what the limit's equal to, provided that f, g, and h have limits as t approaches a. Right, now, obviously, like if g doesn't have a limit here, then the limit of the overall vector valued function would not exist. Right, all three of the components have to have limits in order for the overall limit to work. Okay. Hopefully that makes sense. I think that's pretty intuitive when you usually come across it. It makes sense to me. At least when I first heard it, I thought, oh, that's very slick, very nice. Right? Little did I know, we're just beginning to open up Pandora's box. There's a whole class called linear algebra where this kind of stuff is explored in lots of detail. Right? But vectors are interesting things that have a lot in common with the things that you're already familiar with. Okay, so let's talk a little bit about geometrically, like what does it mean for a limit to exist. I'm going to switch pages so I can have extra space for drawing here. I'll leave myself plenty of space. So let's try to imagine this scenario physically, right? So let's say I have some vector L here, and that's just going to be the vector that is the limit. Right, and then I've got my vector r of t, right? So that vector's over here. And between those two vectors, I've got this third vector, right, which we'll call r of t minus L, sorry. R of t minus L, right? So that's just the difference between those two. Okay, now if r of t approaches L as t approaches a, then what should we expect? Well, then we should expect this difference vector, r of t minus L, right? We should expect the length of that, the norm, i.e., to go to 0. Right, as t goes to a. Okay, let's try to draw like what that might look like. Right, so again, just kind of taking the same drawing here, just reproducing it. All right, so here's my initial r of t. Here's L. Okay, now what's going to happen as t gets closer to a? Well, what should happen is r of t should start moving. Right? It should start moving. Right? And so you can kind of think of, you know, this movement being driven by the value of t going to a. A being kind of what drives the change in the vectors, or, you know, subsequent vectors. RT is changing because t is approaching a. Right, and then so here, of course, you've got this is your r of t minus L, right? And so it's shrinking, right? As t approaches a, the vector r of t gets closer and closer to the vector L, and naturally the norm of the difference between these two goes to 0. Okay. So, and then just like with limits that we've discussed in the past, you know, for the limit, you know, for the limit L to exist, right, it's not necessary that R of A be defined, right, or that R of A be equal to L. Okay, so that's just kind of, that's carryover again from how we think about limits of real valued functions, right? Remember, we had lots and lots of examples where we said, hey, if I've got some function that looks like this, it's got a big hole in it, right? I can still talk about the limit as x approaches a of this function f, right? Even though it's not defined, and I know f of x is not equal to, or sorry, the limit as x approaches a of f of x is not equal to f of a, right? Maybe f of a is down here, right? But we were still able to say that the limit exists, right? All we're saying here is the same property holds, right? The limit L, in order for the limit L to exist, it's not necessary that the vector value function R equal L when t is a. It's also like R doesn't even have to be defined at a, right? It just has to be defined for whenever t is very close to a. Okay. All right. Okay, and so this kind of naturally leads to the question of continuity of vector value functions. Okay, so we'll talk. So this next definition really is going to extend the idea of continuity to vector value functions. So definition will say that a vector valued function R is continuous at the point given by t equals a if the limit of R of t exists as t approaches a, and, right, now remember, what's the and from real valued functions? Not only does the limit of R of t exist as t approaches a, but we also say that it has to be equal to R of a. Okay, so it exists and the limit as t approaches a of R of t equals R of a. Okay, so that's just an exact analog of continuity from the standpoint of real valued functions, right? So we're continuous at a point a if the limit of the function exists as t approaches a, and in fact the limit as t approaches a of the function is equal to R, i.e. the function evaluated at a. It's exactly the same as what we get with real valued functions. And then this naturally extends to intervals by basically saying that if every point in the interval is continuous, then the interval is continuous. And so R is continuous on an interval, and I will say, if it is continuous at every point in the interval. All right, yeah, so that's pretty straightforward, hopefully. Yeah, so I mean, basically just an exact replica of what we're kind of used to from real valued functions. Okay, let's do an example. All right, so let's do an example here. Let's say, let's consider r of t, vector valued function, equal to t times the I vector plus a times the j vector plus a squared plus t squared times the k vector, right? So t a and a squared plus t squared. Okay, so consider this function. The question is this function continuous at t equals 0? Is it continuous at t equals 0? Okay. So how do we approach this? What do we do? Well, first of all, let's try to find the limit of this function as t goes to 0. All right, so let's do that first. So the limit as t approaches 0 of r of t, well, we said that's just going to be equal to the limit of the components, right? So it's going to be equal to the limit as t approaches 0 of t times the I vector plus the limit as t approaches 0 of a times the j vector plus the limit as t approaches 0 of a squared plus t squared times k vector, right? So just those three individual limits. And so what do we get here? The limit as t approaches 0 of just t. Well, we know t is just straight line, so we know that that's just going to be 0. And what do we get here? The limit as t approaches 0 of the constant function a. Well, that's just a. And what happens over here? Well, here you get the limit as t approaches 0 of a squared plus t squared. The a squared term is a constant, right? And the t squared term is the one that can vary, right? So as we get closer and closer to 0, the t squared piece of that expression goes to 0. And so this is just a squared times the k vector, right? So let's write this really succinctly. This is 0a squared, isn't it? Okay, perfect. And so that's the limit. That's the limit of this function as t goes to 0. Now, what happens when we do a straight evaluation of r at 0? So what is the vector valued function r evaluated at 0? What do we get? Well, it's just 0 times the I vector plus a times the j vector plus a squared plus 0 times the k vector. And so there again we get 0a squared, right? And so these two being equal, that means, first of all, the limit existing, and then these two being equal means that r is continuous at t equals 0, which is kind of what we're asked. Okay. All right. Okay, so fairly short lecture, but a lot of very important information. So we know what a vector valued function is now, right? We know what they look like, and we know that they obey many of the same properties of real valued functions, right? Basically due to linearity. They the concept of a limit exists. Limits of vector valued functions. Okay, and we now talked about what it means for a vector valued function to be continuous. Continuity of VVFs. Okay, and so this is kind of enough information to get us started on derivatives and integrals of vector valued functions, and that's what we'll do. That's what we'll tackle next time. We'll talk about how do we differentiate and integrate vector valued functions. Okay, and that'll get us back into calculus, but now calculus of so basically vector calculus, 3D calculus. Okay, so that's where we'll leave it this time, and we'll see you all. We'll see you all next time. Take care.